Okay, and we're starting. So, an announcement before we begin. Test 3. The first. Yeah, so that's May 1st. So that's like a week and a half from now. That's a Tuesday. Yeah, so that's a Tuesday. Test 4. Whatever the last day of class is.
16th.
It's a Tuesday.
Is that the 16th?
Yeah.
Yeah, Tuesday.
Okay, so May 16th.
Well, it's the 15th.
Double check that.
No. No.
It's
It isn't
15th.
the 15th.
It's a 15th, but yeah.
That's a lot of time. I'm willing to do this the 3rd. I wouldn't grade until that weekend anyway, but
No.
No.
would that be better?
Yes.
No, it's fine.
You have another exam?
After?
No project that day.
No, keep it on the first.
Yeah.
Keep it on the first.
I'm gonna do it the 3rd.
Yeah,
Because that'll be at least a week until after I finish the topics that I would need for that test. So I'm gonna finish everything we need for that test by Tuesday of next week. So the following Tuesday. Yeah.
When is the final exam in this class?
The last day.
I believe. I think it's in the syllabus. I don't remember what it is.
24th. It's like the last day.
It's the last day of the finals.
Yeah, on Thursday.
we can end our semester with
For
you.
3.
As long as I get your extra points.
At least
Yeah.
you do.
You're probably
Yeah,
not
so-
gonna be there, right?
Are you gonna send that guy with the fucking
Yeah, so
mustache
it's
again?
May 22nd. The final is May 22nd.
No, isn't it 24th? Is it 24th?
This is. Oh, I'm looking at my other class. It's 346. Okay, hold on.
We really are the last people you see.
Yeah, jeez. Yeah, in terms of the location, I don't know because you guys will actually be doing the departmental final. So I don't know the location, but it's May 24th.
At what time?
Final, May 24th. I mean, it's in the syllabus. I mean, I'm really copying it. And it's actually, it's at a weird time. So it's 3:30. So you need to make sure. Location, I don't know. So they'll have to do some arrangement because you guys will be in a big room with other classes, I assume. But yeah, so that's kind of the layout for the test coming up.
Can I keep the final at own home?
Test 4 especially, students tend to do very well on this. The topics will be easy. Test 3 is also mostly going to be easy. There's going to be a divergence theorem problem, but other than that, it's going to be matrices. No, Stokes theorem was on.
Test 3.
Yeah.
Oh, you don't have to put it in there.
Yeah, you don't have to put it in there.
I'll give you the review. You'll see what's coming up. And yeah, but test 3 and 4, they're good chance, especially test 4. It's a good chance to kind of make up some points there. And let's actually.
Does that mean you're gonna put like a super hard question for your divergence?
Normal questions. There was actually normal questions.
Yeah, your normal questions are hard.
Anyway,
Prove calculus exists. Professor, from the bonus point, for example, if you get 100 on the exam, 3 exam if you get 100, right? And if you get like 20, 20 and 20 on the bonus, and for example, if we screwed up the final, can you add the
no,
bonus?
test 4.
No?
There's no extra credit for the final, no extra stuff for the final, no. So if you get over 100 on any one of the tests, I can add those points to another test, but it's not.
Our
section of the final does better than everyone else.
Huh?
Do we get a curve?
I can give you one between these two if you want.
Give what?
You look so sad. Okay, I'll give you more quizzes.
Why would you do this?
I can only go
This
up
is
in
chapter
grade.
1.
It's not going down.
I think this is chapter 2. Chapter 2 continued.
You were doing 1.2 last time.
Are you sure?
Yes.
Yeah. That's what you stopped.
1.2?
Augmented matrix. That was the last thing you spoke about.
Oh, and that's 1.2?
That's what
I
you
thought that was
said.
chapter 2.
Oh. That's what you
Well,
wrote.
We're doing systems. Sometimes I don't write the section number all the time. Systems of linear equations is what we're going to talk about today. Talk about how to solve them and about the kind of solutions that they can have, and that might spill into next week. So we recall you can be given a system, so let's say an n by m or whatever. 1, 1 is 1 plus a1, 2 is 2 plus one, and a1 plus a2 is 2 plus a2 and you can have a bunch of equations like this, so that m1 all the way down to a. So given that, we can write in what's so-called matrix form, right? Which is more of like a proving device. It's not really the form you're going to use to solve something in general. It's more the augmented form. So that's where you write it like AX equals B. Or you can write it in augmented form, which is usually what we're going to use to solve systems. And that's where you write like one huge matrix where the A matrix goes here, and on that side there's the B matrix. Where A is your coefficient matrix, the A is going to be the A11 or A1n, AM1, AMN. Your X is going to be the solution matrix, and your B is going to be what's called a constant matrix. Okay, so that's where we kind of stopped off last time, just the definition. Yeah?
So in what situation we put the vector notation on the, because you put the vector notation on the X and B but not A?
Because A is representing a matrix, whereas these guys, if you have, this here is an n by 1 matrix. When one of the dimensions is 1, you call it a vector, and you put it's customary to put a dash over it, because you kind of think of it as equivalent to vectors from Cal 3.
It doesn't matter if it's row vector or column.
No, because you can kind of switch them. But yeah, if it's n by 1 or 1 by n, you call it a vector, and they usually put this little thing over it. If it's a matrix, they just call it an uppercase letter. Sort of a customary kind of thing. So now we're going to show you, well, I'm going to show you another way to deal with systems of equations. Okay, so let's So I want you to remember the elimination method. What we're going to be using is mostly going to be based on that method, so I just want you to remember how to do it. So say you wanted to solve this guy. Here. 3x minus y equals 7, and x plus 2y equals 7. Now if you're using the elimination method, what are some of the things you would do?
Find the coefficient,
Do what?
multiply the top by 2.
Okay, so you'd want to multiply the top by 2. Okay, so one thing you would do is you would number these equations probably, just do that. So I can multiply the top by 2, and what would that give us? That would give us 6x minus 2y equals 14. Is equation 1 times 2.
Professor,
Yes,
top by 2.
the top
Oh,
equation.
okay. Can you multiply the bottom by -3?
You could also
Oh,
do
okay,
that.
alright. I did not see that.
Right, this is just the second equation. This is one way. In this case, what we're doing, you notice, is that we're trying to eliminate the y. To do what you are doing, we try to eliminate, that's when you want to eliminate the x first. Okay? So what we can do now is we can add these two. Right? And so we have what?
7x equals 28x.
This will add, that would just be 0y. This would be 28. 21? Who said 28? Someone said 28. And so now you actually have an equation you can solve for x, right? And this was an elimination, what you did. Now I'm going to do this I'm going to redo this in sort of a weird way, and you're going to try to see why. Because I'm going to want to draw a comparison. So notice that there was actually no, of course from this, we could see that x would be equal to 3, right? And then this would mean, you can recopy one of the other equations, right? So if x plus 2y equals 7, this would mean that 3 plus 2 times y equals 7. And from that you can get y equals 2. Okay, so you can ultimately find the solution using the elimination. Now, one thing I want you to realize, as Kaka brought up, that there's no unique way to do this. You could have eliminated the x first. You could do random things. Right, so we could have done something like let's say here, 3 times y equals 7, x plus 2y equals 7. Okay, so I could do something like, you know what? I don't like that equation is not as aesthetic to me at the top as it would be. So I can randomly just want to switch these two equations. And nothing would be wrong with me doing that. Okay, I just want to write, it looks better to me with x at the top. And then I could do what Kakab suggested, and I can, let's say I wanted to eliminate the x first, what would I do?
Top by -3.
I can multiply the top by -3.
So that will be -3x plus, -21. Yeah.
Okay, this guy stays.
So that would be -7y over equal to -14.
Yeah, so let's say I add these two and I make a new equation. So this would be 0.
0.
This would be -7y. This would be
-14.
-14. And I know I'm going to need the other guy. Well, I'm going to keep the first guy because I know I'm going to want to substitute eventually. Let me put this down here. I'm going to keep this because I want to substitute. But when I add these, I'm going to get 0x. I'm going to get -7y. I'm going to get -14. Right? I'm just keeping the pairs together here. And so from this though, I can stop here because in this equation, there's only the y. Right? In fact, if I wanted to make it even nicer, I could just divide both sides by -7. And I would get y equals 2 right away. And from here, I can just say y equals 2. What if I wanted to continue? I know we could back substitute at this point, but let's say I want to keep doing elimination. we could substitute here. But let's keep going. You're gonna see why in a bit. So suppose I wanted to do a similar manipulation to get rid of the y and just leave the x by itself.
Multiply by -2.
I can multiply this second equation by -2. So that's still 0x minus 2y equals -4.
X would be equal to 3.
And then what would I do now? I can add these two.
So that would be 0.
So I would have x plus 0y equals 3. And I actually had 0x plus y equals 2. Right? And so you see in this form here, I basically have x equals 3, y equals 2. Right? It's clear at that point. So it's like, I force myself to keep doing elimination. I don't really stop anywhere and substitute. This is kind of what it would look like to solve the system. At the end of the day, I could get this. Right? And there's nothing wrong with doing it the way I did it. There are multiple ways. You could have eliminated the x first, you can eliminate the y first. There are many choices. But at the end of the day, all choices would kind of lead you to this. The answer is not going to change, right? We're doing things that are mathematically valid. They're not changing the solution set. And so that would be the answer. That's where you'd end up no matter which way you actually pick to get to that root. Okay, so those are two things that you should be aware of. Secondly, can I erase this? Up?
Yes.
Here's an idea. Suppose we augmented this guy. And it was 3x minus 3x minus y equals 7, x plus 2y equals 7. Right? The augmented form would be what?
3, -1, 7. 1, 2, 7.
1, 2.
Okay? That would be the augmented form of the matrix. Now, what's important for you to realize is this represents the system. Okay. And what that means anything that was valid for me to do to the system is theoretically valid for me to do to the augmented matrix. Seems to make sense. Notice here, how is this similar to the system? Is that the rows represent the equations from the original. And so what that means is if I do operations with equations, it's somehow equivalent to doing operations on rows. So let's actually keep things written this way, where we're just moving the numbers around, and kind of repeat the process that we did just a while ago. So I have this guy, 3 minus 1, 7, 1, 2, 7. One thing I did was, for aesthetic reasons, pretty much, I swapped these two. I swapped the order of the equations, and that didn't change anything, so that was perfectly valid for me to do, right? So what I did was, if this is the original that I call row 1 and this is row 2, what I just did is I flipped them. I put row 2 up here and I put row 1 down here.
Wait,
Right?
what did you do? Can you explain one more time?
This is row 1,
Uh-huh.
that's row 2.
Okay, so row 1, row 2. Okay.
Yes.
3, -1, 7, 1, 2. Okay, alright, okay, yeah.
And I just swapped them,
Oh, why do you swap them?
because I felt like it. We did that before. It's not going to change the answer, is it? I did that right here. You never, weren't you paying attention?
I don't remember that.
It's because you're not writing it down. I swapped the 2 rows. Row 2 is now in the top position, row 1 is now in the bottom position. Okay? What was the next thing that we did?
Multiply.
We tried to eliminate the x, right? That's what we did. And how did we eliminate the x?
Multiply row 1.
I multiplied the first equation by -3. Let's actually do
Oh,
that
yes,
here.
yeah, yeah.
Multiply the first row by -3.
Oh, it's...
So here I take row 1 times -3. When I label the rows, the convention that I used is that the label at each step refers to from the previous step. So the row 1 I'm referring to here is actually the first row from the previous step. People label it otherwise, but it's a good way that you label it so you can keep track of what you're doing, because we're going to do things with larger matrices than these, and you're going to want to keep track of what you're doing. Okay? So we did that. And then what did we do?
We added the rows.
I added these guys, right? And what I did was I changed the second equation. When I add these two, I got a 0. When I add these two, I got a -7. When I added these two, I got a -14. And I brought this row back.
Oh, okay.
So we're just kind of, you can look side by side when I did the equations and notice that I'm doing the same thing here. Okay. Now, here, to solve for y, I wanted its coefficient to be 1, right? So basically what I did here was row 1 -3, and here I did row 1 plus row 2. And here, eventually what I did was I took row 2 and divided by -7. Row 1 I think I left alone for a while, and we got here, right? And at this point is where I said, yeah, we could see that y equals 2, and then we could substitute here, but we kept going, right? So we kept going. And then what did we want to do? We wanted to get an equation similar to this in the top, so that I could solve for the x. So what I wanted to do, since this represents the coefficient of y, I wanted to kill that coefficient. And so what we did was we multiplied this second row by -2. And then I added them. So 1 plus 0 is 1, this plus this is 0, this plus this, is that right? I divide by 7, we got y equals 2, and then, oh, this is 4, okay. Where is that? And then we added these guys, and so that gave us 3 here. And 2 here. Now what you can see here is that this last row here, this actually represents an equation. It in fact represents 1x plus 0y equals 3. This row here also represents an equation. It represents 0x plus 1y equals 2. And the nice thing about this matrix is, because I know the x, the first column is the x column, the second column is the y column, I can read this row as just x equals 3. I can read the second row as y equals 2. Right? Because in the background they represent equations. So even though I'm looking at like a rectangular array of numbers, I put an interpretation on this rectangular array of numbers to be that each row represents an equation, where the first number is telling me the coefficient of the x in the equation, second number is telling me the coefficient of the y in the equation, and the 7 is the guy on the other side of the equal sign.
Professor,
Yes?
well, if we know how to like solve the using like elimination, why do we need to do it by like this?
Okay. That's a fair question. That's a very good question. Okay. So suppose And honestly, this did seem a lot more complicated than it would be, back in algebra class. But what if I asked you to solve this?
You're gonna write 6 equations.
I'm gonna I think, do I have to finish writing this out for you to get the point?
No.
When you start eliminating and back substituting and blah, 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 if you don't have like a systematic way of writing things down, it can get into a huge mess in a hurry, right? However, if you ignore the variables and having to match things up really, and just kind of think of it as a way that, oh, I'm just trying to eliminate things to get 0, it becomes more of a streamlined process, right? And when, for example, someone said put it in MATLAB, when you ask MATLAB to solve a system of equations, it doesn't try to match up variables and match x with x. It translates it into just an array of numbers. And then it's just a bunch of arithmetic, and it can solve any system. And when it comes to like huge systems, like the kind of system that you're using MATLAB for is like equations with thousands of variables. It's not going to be something that simple. But it can do mathematical operations on the numbers, right? Just gets rid of the variables, writes it at an array of numbers. It's a computer, arrays of numbers. It's more than equipped to deal with. It goes through this systematic process. It will have some sort of algorithm that tells it how to get zeros into the right positions. But ultimately, we'll end up with a state like this, where then it can output the solution to you. Okay? So it doesn't really have to think, what do I want to eliminate first? What variable do I want to solve for and substitute in that variable? There's a process there that's very thought intensive and computational intensive. And whereas for the 2x2 case, you won't see it as a big deal. When things get bigger and bigger, it becomes a big deal. But the idea is, there was actually a process I was going through here. There was some sort of algorithm in my head, which is why I was doing these things that might have seemed weird before. Like, why did I have to switch those two? Right? There was a reason. And that's kind of what we're going to describe here. So the idea is, given a system, you can augment the system, put it in a matrix form. You can do a bunch of operations in a very systematic way to end up with a solution. And you can do this for things of any size in theory, right? Now, there are times when there's no solution. There are times when there are actually infinitely many solutions, and we're going to discuss that in the next chapter. But for now, we're going to talk about what I just did here. How did I do that? Why did we want to solve it this way? And the form that I ended up with, this guy that I wanted to do, where each row had a 1 in the position of the variable I wanted to solve for, and a 0 in the position of all the other variables that I didn't want to solve for. That's a very convenient form. That's going to be a form that we're going to like to get to. And it has a name, right? So the form this is generally described as the so-called reduced row echelon form. It is a form that is convenient when finding solutions. Right? The idea is get a 1 in the position of the variable you want to solve for, zeros everywhere else in the row, and then the answer will be at the end, and that will actually give you the answer for that variable. Every row you try to do this. This is the ideal case. Every row will have that kind of structure.
So sir, what is that word reduced row?
This?
Yeah.
Reduced row, this is echelon. Echelon. That's the name of the form. It's called the reduced row echelon form. I'm gonna actually derive. I forgot what the etymology is. I think it's German or something.
I thought it was like a Roman soldier that stood in like rows and columns.
Huh?
Echelon?
Echelon?
Yeah.
Isn't that a German-based word?
Probably. Everything from math comes.
Not really.
Fibonacci.
Almost every word.
Fibonacci. Okay, let's go. So let's actually talk about these, the echelon forms. There are actually a couple that we care about. So when we put a matrix in augmented form, and the purpose of that augmented form is to solve a system of equations, the echelon forms are the guys we will want to get into. There are two. One is called the row echelon form. The second is called the reduced row echelon. Row echelon form is, in previous example, do you remember we got to a point where we already solved for the y, but the x wasn't solved for? What was it? It was 1, 2, 7? Right?
Yep.
That was something that's known as row echelon form, right? Where some guys I have solved for, but to find the other guys I had to do a back substitution, right? But it's in a pretty nice form to deal with anyway. The row echelon form is when something that happens in the last line happens for everybody, right? So this would require some extra work. Some more substitution has to happen, which when you're doing it by hand, if the point is to solve the system, it's perfectly fine to stop here. This you can read solutions off directly. So if a computer is doing it, a computer will go all the way to here, but a human doesn't have to go all the way.
So for the second one, is like you're trying to get the left side into the identity matrix for reduced row echelon?
Yes, that is the ideal. You're trying to get to the identity matrix.
And then the other one is just like that.
And the other one
It's
is
just you solving until you
it's
can
just
access
it's a
it.
point that's good enough to find the solution. This is a point where the goal would be to try to reduce the left side into the identity matrix so that you can read off the solutions very easily. But it turns out that that can't always happen, so I'm going to describe these forms. And it turns out there are only 3 situations that can happen when you try to attempt to reach one of these 2 forms. And that's going to determine how your solution to the system will look. So let me describe them. 1, row echelon form. Of an augmented matrix. A matrix is said to be in row echelon form if the following, and I might, because I don't like writing that out, so I might abbreviate this RREF. If the following criteria hold. 1, any row of zeros is moved to the bottom of the matrix. You might not have a row of zeros, but if a row of zeros occurs, move them all to the bottom. Why we can do that is because we can always switch equations. It's not going to change our solution set. 2. First non-zero number in each row is a 1. Right? Why? Because we want to get the first digit to be the coefficient of the variable that we care about. We want it to be a 1. And I also call this a name. This is called a pivot or leading 1. So in this situation, I would call this guy and this guy a pivot. This is the pivot in the first column, this is the pivot in the second column. Okay. So any row of zeros move into the bottom. The first non-zero number in each row, you should try to make it a 1. And that's called a pivot. Now I want the pivots to be arranged in a certain way. Again, as Naomi said, we're trying to model the identity matrix because that's an easy way to see the solutions. Pivots, of course, except in the top row. Should be to the right of the pivots in higher rows. Okay. So notice here, the pivot in the second row is to the right of the pivot in the first row. That's pretty much it, but I can do an extra description here. Pivots, pivots, except in the last row. Must have zeros below them. In their column. Right? So for example, here's a pivot. I want the guy below it to be a 0. Right? X is going to be the subject of my formula in the first equation. I don't want him showing up in other equations, because then that's just extra back substitution for me to do. And that's it. A matrix is said to be in row echelon form if it fulfills these criteria. You'll notice that this matrix fulfills all those criteria.
Wait. Okay, done.
Now I'm going to describe to you reduced row echelon form. I'm going to describe to you how we get things in this form. We might have time for a couple examples.
Question?
Yes.
Understand what is rule number 1?
Any row of zeros is moved to the bottom. If I have a row where there's a 0, 0, 0, 0, 0, 0, 0, make sure it's at the bottom. Reduced row echelon form. RREF. The matrix is said to be in reduced row echelon form if 1, it is already in row echelon form. With an additional criteria. Right, so if you want to get to reduced row echelon form, first get to row echelon form. Be criterion. Here's the additional criteria. Every pivot except in the top row should also have zeros above them. Notice in here, here's a pivot that's in the second row. Above it is a 0. i.e., pivots are the only non-zero numbers in any column. In their column. And once you go that far, you're set to be reduced or echelon form. We can make a note here. The RREF form of a matrix is not unique in general. But its reduced or echelon form is. So it's possible for me to give you a matrix equation, actually to put it in row echelon form, and everyone in the class has a different looking answer. If I ask you to put it in reduced row echelon form though, everyone has to have exactly the same answer, if it's the right answer. So for a given matrix, its reduced or echelon form is unique. There will only be one way to write it in reduced or echelon form. This is not true for row echelon form. So now the question is, how do we get a matrix in this form? And the answer is something I said before. They're called row operations. And these are operations on rows that do not change the solution set. So anything you can do with a set of equations and not mess up the answer, you can do with rows and not mess up the answer. And when you do these are called row operations. And we are also going to classify those because it's going to be important.
Zero. 1 second.
1 second over.
Where are you?
Pivots.
You're here?
Yeah. And 0. Okay, done.
There are 3 standard row operations. They're called elementary row operations. Essentially, there are 3 things you can do to the equations in a system of equations and not change the answer. Right? Anything else you do is a combination of these. This is why these guys are called the elementary row operations. If you do something that's not listed here, what you actually did was a combination of the things that were listed here. There are only 3 things you can do to an equation and not change the answer to that equation, to that system. So there's what's called a type 1 row operation. And this is swapping 2 rows. Similarly, if you have a system of equation, you swapping the order in which you wrote the equations doesn't change the answer. So swapping the order of rows, 2 rows, does not change the answer. This is an elementary row operation. So you're given a system, if you reorder how the equations are written, doesn't make a difference. So given an augmented matrix, reorder the ways the rows are written, doesn't make a difference in terms of the solution. Yeah?
So it's not just 2 rows, but any rows?
Huh?
So if you have multiple equations, you just swap around?
Yeah, but if you're swapping a bunch of rows, you're really doing it 2 at a time. I'm talking about elementary, right? We're talking about doing one thing, right? You can swap 2 rows. And then you can swap 2 rows again. Then you can swap 2 rows again. You can interchange the rows in any order you want, ultimately. But that comes down to swapping 2 rows. There's also what we call a type 2 row operation. And this is multiplying a row by a non-zero constant. Right? This is why we could like multiply this equation by -2 and then add it to that, right? When we multiply by -2, we weren't worried about it because multiplying both sides of an equation by -2 is not going to change the solutions to that equation. Right? If x equals 3, it's also true that 2x equals 6. They're both true at the same time. You're not going to kill the answer. It has to be non-zero. Like if I have x equals 3, you multiply both sides by 0, you've lost all information. I don't know what I was even talking about anymore. Everything just says 0 equals 0, right? So you can multiply an equation by a non-zero number, it will not change the solution, and so therefore you can do the same thing with a row. You can multiply a row by a non-zero number, and it won't change the solution. The third type is the kind of row operation that allows you to do the elimination process. Basically, add a multiple of one row to another row to kill something. Okay? This is called a type 3. Now, it is going to be carefully phrased here, and there's a reason why it's carefully phrased. One of the reasons is when we get to determinants, we're going to talk about how these types affect determinants, and it's going to depend on how this is phrased exactly. In practice, you don't have to think of it this way, but when you think of it as an elementary operation, this is how you think of it. Replace a row by itself plus a multiple of another row. This is basically elimination, right? You add a multiple of one row to another. But the way the type 3 is phrased, there's a specific reason it's phrased like this. In chapter 4, we'll see the why. But yeah, that's called a type 3 row operation. This is the elimination method, essentially. So I can replace a row by itself, plus adding a multiple of another row to that guy. It's not going to change the answer. This is the elimination. That's called a type 3 row operation. So the idea here given an augmented system, we can use row operations to get it into one of the echelon forms. And hence solve the system. As well as we can make other conclusions, and we're going to do a few of them here. Row operations are super useful. You don't actually only do them in the context of solving equations, but in this class, that's pretty much what we're going to use them for. Well, we're going to use them to help us find determinants as well. So we'll see a couple uses of row operations, but this is the main one that we're going to use in this class. Given a system, write an augmented form, use row operations to get it into a form that you can see the answer to the system. And we'll make some other conclusions as well later on. Let's do an example. Or maybe, do I want to do that first or? I don't know which one I want to do first. Maybe recognizing them. Let's just do that. Not really a computational question, but just recognizing. And then we'll do some computation. This should go by easy, but it's always nice to know when you're actually doing a problem to know where you should end up, what the answer should kind of look like, and to know when you can stop versus when you have to keep going. That's a common thing. So here's an example. Basically tell me if this is in row echelon form, reduced row echelon form, or neither. So here are the examples. 1, 2, 0, 1. Okay. I wish I had some colored chalk to point out the differences. Anyway, first one. Row echelon form, reduced row echelon form. This is row echelon form. What makes it not reduced row echelon form? The 2 shouldn't be there, right? If that 2 were a 0, it would be in reduced row echelon form. But as it is written, it's row echelon form. What about this one?
Neither.
No, it's REF, right?
Neither.
Neither.
It's row.
It's all
Is RREF.
No, just REF.
Because only
It's REF.
wait. Yeah. And then it has 0 on the top. Is RREF.
No, it's just REF.
See what you're looking at us.
It's RREF.
Why?
You tell me. What are the criteria?
Zeros are at the
Rows
bottom.
of zeros are all at the bottom.
Anything above and below.
First non-zero number in any row is a 1.
Anything below and above is a 0.
Anything below a pivot is a 0. And the final step is that all pivots must also have zeros above them. So in the columns where there are pivots, the pivots are the only non-zero numbers.
Brother, what do you
This
mean?
fulfills all criteria.
What do you mean with pivots? I did not get that part yet.
The pivots is the ones. These guys are called pivots. The first non-zero number in each row is just called a pivot. So that's reduced row echelon.
So one is a pivot and that one is a pivot because it's under
Yes,
the
pivot
zero.
in the first row, pivot in the second row.
Okay.
From left to right, this is the first non-zero number you hit, and it's a
Okay.
1. It's called a pivot.
Okay.
What about this one?
Neither.
Neither.
It's
Neither. Why?
The one below the one.
Because this one. This guy's a pivot in the second row. He's the first non-zero number, but he's 1. He's not to the right of the guy that's above him, so that's 1. And second, there's no zeros above him, and he's the second row. What about this one?
REF.
RREF.
That's REF. Why? Because this 2 kind of messed it up. If that were a 0, it would be reduced or echelon form. What about this one?
Neither.
Neither. Is it that 2? This one? Neither. Why?
Zero.
Because of this guy. Any row of zeros should be at the bottom. This guy? Reduced row echelon form.
REF.
Just row echelon form. Right? Row of zeros at the bottom. The first non-zero number in each row is a 1. All of these guys occur to the right of the one that's above them. And by the way, it doesn't have to be immediately to the right. I don't want you to take that interpretation. So, in fact, I could say this is also a reduced or echelon form. So when I said to the right of the one above them, it doesn't have to be immediately to the right. It doesn't have to be in this position. It can be as long as it's to the right. The problem that this is not reduced or echelon form is because the 7 is here, the 2 and the 7 here. I have numbers above these guys that aren't 0. So that makes it not reduced. Let's actually run through an example of putting a matrix into reduced or echelon form. So the idea is here, you are going to have to do it by hand in this class, unfortunately. So, and there's, as I said, there's no unique way to do this. So I want to give you like a more efficient way, so you don't end up taking 15 steps to do something where it could take 3 steps, because it's very possible to end up in that situation.
Can we use calculator for final?
No. So, example, put in reduced row echelon form. So here's the matrix. Don't worry about whether it represents a system or not our concern. I just want you to put it in the right form. That's your matrix. Reduce or echelon form. Go. What would you do first? What would you do second?
Swap row 1 and 2.
I'd swap row 1 and 2. Right? Good. That makes a lot of sense to do that. Okay, there's something I'm going to want to do. So I'm going to put, what I'm going to write here is I'm going to put row 1, row 2 here. Right, so row 2 from the previous step, I moved it up to row 1. Why? I'm establishing the top pivot, right? And I know this has to be the farthest to the left than any other pivot. And since this guy already has a 1 in that position, I just moved him up there to make him the upper guy, right? I don't know if I want to write these. moved row 2 to get top pivot. Okay, now there's going to be an algorithm here. This is kind of how, when you're doing it by hand, you're not a computer, you're not using a calculator, there are going to be better ways and less efficient ways. Once you do that, your goal should now be to immediately get zeros below this pivot. Which means, when you take one step, you should be in a position where that is the result. Yes?
I think I got it. The next step.
Sure. What would you put here?
Well, so you take row 2 and you multiply it by 2 and then you add it to row 1.
Yeah, doing that would give me a 0 here. So multiply this by 2 and add it to that would give me a 0. Multiply this by 2, add it to that.
5.
5. Multiply this by 2, add it to that.
5.
Multiply this by 2, add it to that.
30.
So that would be the second line. Whatever I'm doing, I want to get a 0 here. So what is another option? You just use row 1 and row 2, so using them again is not going to work. Right? You have to use 2 other rows, but whatever you do, it must be a row operation, it must be legal, and it must also give us a 0 here. What's another option?
Row 3 by negative, multiply row 3 by negative 3 and add it to row 1. Wait, what? What did I say? I don't know.
Oh, the labeling
I
I'm
said it
using is referring
backwards.
to the first one.
Right.
So I think you want to multiply this by negative 3 and add it
Yes,
to that.
there you go.
Right, so I can say something like row 3 minus 3 row 2 from the previous step. I label them based on how they look in
Okay.
the previous step.
Do you have to label them on the test?
I would recommend you do. Because let's say you don't and you get to the wrong answer, I'm not going to go check over all these numbers to see where you went wrong. I'm just like, okay, 0. I don't know what you were doing, if it makes any sense at all. But if you're writing down what you're doing, I can check your steps. It's also good for you. There are times when you're going to know what your answer should look like. And so when you actually, you know you made a mistake, you can actually go back and track what you did and that it should be the same. So what I'm going to do is I'm going to take this minus 3 times that, 0. This minus 3 times that. This minus 3 times that. This minus 3 times that. That's right, right? Yeah?
For this situation, can we use like negative row 2 plus 1 row 1? Can we use this?
For this one,
Yes.
take 2 times this.
No, negative row 2, like what becomes negative 1, and then
Okay.
plus 1 of the row 1, which is negative 2. So the sum of the
Take negative 1 times this and then add what?
no negative 1
Times this? Times
plus
this one?
plus row 1.
So row 3 minus row 2 plus row 1 should give a 0 in the bottom right.
So you want to
do a
do,
combination of the 2 rows.
Can we use this?
oh, sure. But that looks like you did like 2 things at a time. I don't think
You can do it.
Professor,
But
You can,
for
but
the third row, will be give the
wait, this does not have to be.
anyway, let's move on.
As long as
I'm not
you
exactly
have
sure.
one here, 0.
Okay, so the next step, once you've established the topmost pivot, the next step would be to establish the pivot in the next row down. So it means I'm going to want to turn this guy into a pivot. So I'm thinking of what's the quickest way to turn that into a pivot?
Divide by 5.
Divide by 5. I'm going to take row 2, divide by 5. This is just the old row 1. So since I established this as a pivot, I immediately want a 0 here. Right? I'm going to do the same process. Once I get a pivot, I want a 0 below it. So how can I get that 0?
Multiply, say,
Row 1. Row 1.
What if I can take this times 6 and add it to this? Right? That would create a 0.
Excuse me, please. When do you think you will finish?
A couple minutes. So if we do that, what would we get?
Wait, what you said?
I'm going to take this
Right.
and multiply by 6. So I'm going to think of it as 6, 6, 12.
Okay.
And I'm going to add it to this.
Okay.
Negative
So negative 2.
0,
And negative 4.
2.
So this is 6 plus this, right? Which would be negative 2. And 12 plus this.
38. No, what?
You said times 6.
Huh?
36. Oh, yeah.
Yeah, 36 plus minus 40.
Negative 4.
And then divide by 2. By
And
negative
what
2.
I just did was 6 times rho 2 over 5 minus, well, plus rho 3. So 1, 2, 3, 13, 0, 1, 1, 6.
Divide the last row by negative 2.
Rho 3 divided by minus 2 gives me 0, 0, 1, 2.
Row echelon.
So that's in row echelon, right? So we want to go a little bit further. So by the way, this is row echelon form. We're going to keep going because that form is not unique. So which means I want to kill this and I want to kill that and that. Let's kill this one first. Right, at this point it kind of doesn't matter what order you want to do it. So I can just take here row 2 minus row 3. Right, so this is 0, 0, 1, 2. I can take this minus this, 0, this minus this, 1, this minus this, 0, this minus this, 4. And I don't want to do this. And what I can do here, we'll need one more step. I can take row 1 minus 3 row 3. I'm worried about killing this. This minus this, 1, this minus this, 2. This minus 3 times that, 0. This minus 3 times that is what?
7.
7. We're almost there. This is the last one. So now to just kill that, I can just take this row minus 2 times that row, right? So it's row 1 minus 2 times row 2. And this would be 3 minus 2 times that. Well, that's just 3.
No?
Or,
0.
oh, that,
Whoa.
I'm doing 1 minus 0. I was looking at this line. 1 minus 2 times this, 2 minus 2 times that, this minus that. That would also be 0. And this minus 2 times that gives me what? And I think the rest are okay. And so that would be your answer. Anyway, we'll stop there. We'll do a lot more of these.
This is like so much.